4 starts out with proof by contradiction, essentially proving something's true because it can't be false. It's kind of an interesting way of looking at things, but anyway, let's go ahead and take a. I might have actually even misspoke on that. I don't know. So let's go ahead and look. Here's how Coach Thompson, one of our old math teachers and tennis coaches, used to go ahead and introduce this lesson, and I like the way he does it better than the Foursquare game. So let's go ahead and take a look here. There we go. So he started with Sudoku. I don't know if you guys know the game of Sudoku. This is a pretty simple version of it where there's only 6 numbers. Sudoku is usually 9 by 9, but long story short is you can only put the numbers 1 through 6 in each row, the numbers 1 through 6 in each column, and the numbers 1 through 6 in each box. Which means if we start here is 1, 2, 4, 5, 6. Well, this has to be a 3 because I'm not allowed to use the numbers 1, 2, 3, 1, 2, 4, 5, or 6 twice, so that's got to be a 3. If I go here 1, 2, 3, this has to be a 4. Right? So that's the logic of this game. And the same thing is true of columns. 1, 2, 3, 4, 5. This must be a 6. And that's sort of how this game goes. So it's kind of a fun game. Kids usually enjoy it. You can start to fill it in. Like, I know that this can't be a 2 because I already have a 2 in this row. So either of these ones looks like it could be 2, so I don't know what to do there yet. I know this can't be a 3. So either of these could be a 3, 4, 5, 6. Well, I know this can't be a 6. This can't be a 6. This can't be a 6. So this must be the 6. And again, I know that this has to be the 6 because I already have a 6 in this column. I already have a 6 in this column, and I already have a 6 in this row. So that has to be a 6. So let's see, going back to the 2s, this must be a 2 because I already have a 2 in this row. So 1, 2, 3, 4, 5, 6, and so on and so forth. So you kind of get to play with these. I will go ahead and pause this real quick so you don't want to watch me play Sudoku, but I'll just put the answers up so you have them. Just real quick, to give you the answers. I hope you enjoyed playing Sudoku. Kids usually do. Again, these are simpler versions. You can definitely get a 9 by 9, which is a little bit trickier. But the long story short is you can start by assuming something is true, proving it's false, and you have proved by contradiction that it can't be what you originally thought that it was. So let's go ahead and jump into this section. And again, just sort of using that logic where proving something can't be true is going to help us out. So let's go to proof by contradiction. And again, we didn't do problem 234. We used Sudoku. You first assume that a conjecture was false, and then that assumption led to a contradiction that showed your assumption was false. Therefore, one's conjecture was true. This type of reasoning is proof by contradiction. To prove a conjecture, you must start by assuming it's false. I guess I said the opposite. And then if your assumption leads to an impossibility or a contradiction of other facts, then the conjecture must be true. So yeah, I think I've been saying it wrong. You will use proof by contradiction to prove the converses of some familiar geometric shapes. So in the diagram at right, what is the relationship between x and y? Well, we know if these are parallel lines, these are same side interior angles. It says write a conditional statement or arrow diagram to justify your answer. So if lines are parallel, which they are, then same side interior angles are supplementary, meaning they add to 180 degrees, right? It says write the converse of the theorem used in part A. And by the way, this is true, right? We know that this is true. It says write the converse. If same side interior angles are supplementary, then lines are parallel. And is the converse true? Yeah, we said that. I think we said at the end of 213 that this exact thing would be true, right? If we know that the same side interior angles are supplementary, then that means that the lines have to be parallel. So it says to prove that this converse is true using proof by contradiction, you must start by assuming it's false. For this statement, that means you will assume that the hypothesis that same side interior angles are supplementary is true. So we're going to say, hey, same side interior angles are supplementary is true, but the conclusion is false. We're going to say these lines aren't parallel. So here's what they mean by that. We're going to go over here, we're going to draw, and we're going to say, hey, look, these same side interior angles, these are same side interior angles, and they're supplementary. They add to 180 degrees, but these lines aren't parallel. So what would that look like? Well, here's what that would look like. I would say, hey, look, this is 100 degrees and this is 80 degrees, because what's 100 plus 80? Isn't it 180? And that's what supplementary is. We're saying the lines, we're saying the same side interior angles are supplementary. And then we're saying, are these lines parallel? Well, could this possibly be 0 degrees? It's impossible, right? So by assuming that this was false, we assumed that these lines weren't parallel, and it led to an impossibility. So we proved through contradiction that we can't have these lines not be parallel. They have to be parallel. Otherwise, if they're not parallel, they turn into a triangle, and that means that this degree has to be an angle, which it can't be. It doesn't make sense. So this contradiction allows us to prove this statement has to be true. I hope you guys followed that. It's kind of tricky. We'll do a couple of other ones, and hopefully that makes sense. So let's set up some of the other ones. Proof by contradiction here of what's going on. And again, what we're going to do is we're going to say, hey, prove why these lines must be parallel. So if corresponding angles are congruent, then lines are parallel. So let's go ahead and we're going to prove by contradiction. We're going to say that the first part is true. These corresponding angles are congruent. But the second part is false. Right? We're going to say that these lines are not parallel. Obviously these lines are parallel, but we're going to say that these corresponding angles are congruent. So 80 degrees and 80 degrees. Well, think about it. If this is 80 degrees, these are supplementary angles. These have to be 100 degrees. 100 plus 80, this would have to be 0, which is impossible to get this triangle. So there we go. We assume that the lines weren't parallel, but we assume that the angles were congruent, right? The corresponding angles were congruent. That led to an impossibility. So we can say the statement must be true. If corresponding angles are congruent, then lines are parallel. Like we proved that with contradiction. Well, what about this one? Here, we're going to say, if alternate interior angles are congruent, we're going to assume that's true, then lines are parallel. We're going to assume that's false. So here we go. And geez, I'm going to make the straight line tool, because my goodness, I cannot do this to save my life here. So here we go. We're gonna draw this so that these alternate interior angles here we'll say is 80 degrees. Okay, here we'll say is 80 degrees, and this is 80 degrees. Actually, I guess I should be consistent with what the picture is showing. The picture is showing that this is 80 degrees, and this is 80 degrees, right? We're saying, hey, look, alternate interior angles are congruent, but the lines aren't parallel. The second part we're saying is false. Well, here we go. We have a straight line, and this must be 100 degrees. If this is 100 and this is 80, this can't be 0, so this is impossible. And if this is impossible, we have a contradiction, which means that this is true. So there we go. It says, since you proved the relationships in part A and B, these new relationships can also be called theorems. Write two new theorems that begin, if corresponding angles are congruent, then lines are parallel. And if alternate interior angles are congruent, then lines are parallel. So we know that that's true. If we can just prove that corresponding angles are the same, then we know those lines have to be parallel. If we can just prove the alternate interior angles are the same, then those lines have to be parallel. So we can go ahead and make note of that. We've got some probability coming up, so hopefully we know what probability is, the successful event versus sample space. We'll be getting into that, I think, in a different chapter. I think in chapter 3 we'll be doing some probability. So this is just setting us up for what's to come.